Hello all, myself A. Kalpana, Assistant Professor in Electrical Engineering Department, Mlritm, and designation as Assistant Professor, course name Electromagnetic Fields. Today's topic name is Dielectric Materials and Capacitance. So in the last class I have discussed about the conductors, so how they are behaving in electric field. Today I am going to explain about the dielectric materials and capacitance. So as we know that dielectric materials do not have free electrons and they contain bound charges that cannot conduct electricity. Why? Because in dielectric materials there is no free electrons, so there is no movement of these free electrons. That is the reason this will not conduct electricity. So when electric field is applied to these free electrons, these dielectric materials, these charges slightly shift from their respective positions, means normal positions, and creating separation between the positive and negative charges. This results the formation of electric dipoles, which enables the dielectric to store the energy. Means we have positive charge and negative charge. So these are separated with a very large distance, and whenever electric field applied for this, so it is a dielectric materials. We have no free charges, just we have some charges will be present like this. Whenever we are creating a electric field like this, so these electrons will be moving. So because of that, there is a bound charges are found like this. Okay, so these are nothing but a dielectric dipoles. So these enables the dielectric to store the electrical energy. So next, these properties of dielectric materials. They are dielectric materials do not contain any free charges, but they contain bound charges. Bound charges means positive charge and negative charge like this. And bound charges are under the internal molecular and atomic forces and cannot contribute to the conduction. When subjected to the means, these will not conduct when we create electric field, then only it will conduct. When subjected to the external electric field, these bound charges shift their relative positions, and due to this, a small electric dipoles get induced inside the dielectric. This is called polarization. So due to polarization, the dielectrics can store the energy. So means in dielectrics, we have many bound charges like this. Like this, we have free bound charges. So these will store the energy whenever we are applying external electric field. And due to the polarization, the flux density of the dielectric increases by amount equal to the polarization. And the induced dipoles produce their own electric field and align in the direction of applied electric field. Means align means they will move in a applied electric field. When polarization occurs, the volume charge density is formed inside a dielectric, while the surface charge density is formed over the surface of the dielectric. And the dielectric outside and inside the dielectric gets modified due to the induced electric dipoles. So these are the properties of dielectric materials. Next, coming to the boundary conditions. So first of all, what is boundary? So in electrical terminology, the boundary means whenever the electric field passes from one medium to the other medium, that is called every medium has some boundary. So that is nothing but a boundary. So boundary conditions means when electric field passes from one medium to the other medium, it is important to study the conditions at the boundary between the two mediums. The condition existing at the boundary of two medium when field passes from one medium to the other medium called a boundary condition. So depending on the nature of the medium, there are two boundary situations of the boundary conditions. So one is boundary between the conductor and free space, and boundary between the two dielectrics and different properties. So first, in free space is here boundary between the conductor and free space. Here free space is nothing but a dielectric, hence first case is nothing but here boundary between the conductor and the dielectric. for studying these boundary conditions, we require Maxwell's equations for electrostatics. So here, as from the Maxwell's equation, the closed line integral of E dot dl, here E is the electric field intensity equal to 0, and the closed surface integral of electric flux density is equal to Q, that is charge enclosed by that surface. So similarly, the electric field intensity is required to be decomposed into two components. So one is the normal component and the tangential component. So total electric field is nothing but E equal to tangential component of electric field intensity and normal component of electric field intensity. For same as this, for electric flux density has two components, that is tangential component and normal component. So for to get the boundary conditions between the conductor and free space, for that I am considering boundary between the conductor and the free space. The conductor is ideal and it is having infinite conductivity. We know that. And such conductors are nothing but copper, silver, etc. And these are have the conductivity of 10 power 6 Siemens per meters. So for ideal conductors, it is known as, we know that the electric field inside the conductor is 0 and the flux density inside the conductor is also 0. And next condition is, no charge can exist within a conductor and the charge appears on the surface of the conductor and surface charge, that is in the form of surface charge density. The charge density within the conductor is also 0. So these are the ideal conductor characteristics. Thus, electric field intensity, electric flux density and volume charge density within a conductor is 0, whereas surface charge density is on the surface of the conductor. So to determine the boundary conditions, let us choose a closed path and a Gaussian surface. So this is a closed path ABCD and this is a Gaussian surface. So here we are considering normal component and tangential component. So this is normal component and this is tangential component. For free space and conductor, there is a boundary between these two. So we need to determine what is the electric field intensity for this closed surface and Gaussian surface. First of all, we will calculate what is the electric field intensity at the boundary. So for that, I am considering E is the electric field intensity in the direction shown in the figure like this here. E is the electric field intensity in this direction, and it is resolved into two components. One is the tangential to the surface, one is the normal to the surface. See, tangential surface and normal surface. So this is the equivalent. Here it is known that the line integral of over a closed surface, that is E dot dl equal to 0. Here it is calculated over a closed contour. See here, this one, closed contour. And that is work done in carrying a positive discharge along the closed path is 0. So for that I am considering the rectangular closed path, that is ABCDA as shown in figure, this one. So here I am considering in a clockwise directions, that is A to B, C to D and D to A. Hence total E dot dl equal can be divided into 4 parts. First is from A to B, E dot dl, plus B to C, E dot dl, and C to D, E dot dl, plus D to A, E dot dl. Total electric field intensity over a closed contour is 0. So here I am considering A to B, B to C, C to D and D to A. So here this closed contour is placed in such a way that the two sides AB and CD are parallel to the tangential direction to the surface, while other two are normal surface, parallel surface and normal surface. So at the boundary condition, here the rectangle is an elementary rectangle with elementary height delta H, and the elementary width delta W. The rectangle is spaced in such a way that half of the is within the conductor and half is the free space. Thus, delta H by 2 is within the conductor and delta H by 2 above the free space. So this one, see here. The portion CD is in the conductor here. Within the conductor, as we know that within the conductor is electric field intensity is 0. So the corresponding integral also 0. So the equation 2 can be written as like this. So integral A to B means C to D part is eliminated here. Total 3 parts will be there. That is A to B, B to C and D to A. So as the width is very small, here width is very small. So integral over it can be assumed as a constant and hence it can be taken out of the integration. So that is width is nothing but from A to B. So A to B E dot dl equal to E into delta W. Why? Because it is very small. We are considering it is a constant. No need to take the integration. But delta W is along the tangential direction at the boundary. So this is a tangential direction. So in which direction E equal to E tan means tangential component of electric field intensity. Therefore, integral A to B E dot dl equal to E tan of delta W, where E tan equal to modulus of E tan. So here now B to C is parallel to the this one. B to C is parallel to the normal component. Hence we have E equal to E normal along this direction only. So let E equal to modulus of En. So over the small height delta H, En can be assumed constant and can be taken out of the integration. So for that, so integral B to C E dot dl equal to En E normal of integral B to C dl. So this is the sixth equation. But out of B to C, B to 2 is in free space and 2 to C is within the conductor. Where within the conductor electric field intensity is 0. So integral B to C dl equal to, it is slipped into two parts, that is integral B to 2 dl and plus integral 2 to C dl, that is equal to delta H by 2, and this one component is 0, that is 2 to C component is within the conductor. So where electric field intensity is 0, so that integral B to C dl equal to delta H by 2. So by substituting it in B to C, we will get E normal into delta H by 2. Similarly, for path D to A, the condition is same for the path P to C. So we can write, but it is in the opposite direction. So integral D to A E dot dl equal to minus En into delta H by 2. By substituting all equations, in first equation, this one, in this equation we'll get, so the E tan delta W plus E normal into delta H by 2 minus E normal into delta H by 2 equal to 0. From this will be eliminated. So E tan delta W equal to 0. From this, tangential component of electric field intensity is 0 at the boundary condition. So here the electric field intensity at the boundary between the conductor and free space is always in the direction perpendicular to the boundary. Similarly, for electric flux density, D equal to epsilon naught into E. This is for free space. So that from that we can eliminate D tan, that is flux density, electric flux density in tangential direction equal to epsilon naught into E, that is electric field intensity in tangential direction, that is equal to 0. Thus, the tangential component of electric flux density is 0 at the boundary between the conductor and the free space. So next, normal component we need to find out, that is electric flux density in a normal component at the boundary, or how it will be. To find the normal component of D, select the closed Gaussian surface. We already selected, this is the closed contour, and this is the Gaussian surface. For this component, for this surface, we need to calculate the boundary conditions for electric flux density boundary conditions. See here. So here, so it is in the form of right circular cylinder. Its height is delta H, and it is having surface area, that is delta S. And its height is placed in such a way that the delta H by 2 is within the conductor and remaining delta H by 2 in the free space. Its axis is normal direction to the surface. According to Gauss law, as we know that Gauss law, that is closed electric flux density in a surface area equal to charge enclosed by it. That is, closed surface integral of d dot ds equal to q. The surface integral must be evaluated over the three surfaces here for this Gaussian surface. See, top surface, bottom surface and lateral surfaces. Same as previous, here we are considering A to B, B to C, C to D and D to A. For this Gaussian surface, we are considering top surface, bottom surface and lateral surfaces. See, so total area of the top and bottom is same as to equal to delta S. So integral top into d dot ds plus integral bottom d dot ds plus integral lateral surface d dot ds equal to q. This is the total boundary conditions for normal component. So here the bottom surface is within the conductor, as we know that, but in bottom d equal to 0, that is electric flux density inside the conductor is 0. So hence the corresponding integral is also 0. The top surface is in the free space and we are interested in the boundary condition. Hence top surface can be shifted to the boundary with delta H equal to 0. So therefore, integral top d dot ds plus lateral surface d dot ds equal to q. So the lateral surface area is 2 pi r into delta H. Why? Because it is a Gaussian surface, it is a right circular cylinder. So we know that the area of this is 2 pi r into delta H, where r is the radius of the cylinder. But as delta H tends to 0, this area reduces to 0 and corresponding integral is also 0. So while only the component of D is present in the normal component having magnitude D normal. So the top surface is very small over which dn can be assumed constant here and can be taken out of the integration. So therefore, the integral of top d dot ds equal to d normal of top integral of top ds, that is equal to dn into delta s. So as we know that from the Gauss law, this dn into delta s equal to q, that is total charge enclosed. So, but at the boundary, the charge exists in the form of surface charge density, that is rho s coulomb per meter square. So that this q equal to rho s into delta s. By equating previous equation and this equation, previous equation in the sense 16th equation, this one, dn into delta s, from that we can replace the q by rho s into delta s. From that we can, that is dn equal to rho s. Thus the flux leaves the surface normally and normal component of flux density is equal to the surface charge density. So dn equal to rho s. But dn equal to, in terms of electric field intensity, that is epsilon into E normal. So we can replace this by epsilon into E normal. From that En equal to rho s by epsilon. So this is the normal component of electric field intensity at the free space boundary. So next, coming to the capacitance. So for this, I am considering two conducting materials, that is M1 and M2, which are placed in a dielectric medium having the permittivity of some epsilon, and the material M1 carries the positive charge and M2 carries the negative charge, and these are equal in magnitude and there is no other charges present in a total charge of the system is 0. In the conductors, the charge cannot reside within a conductor. It only resides on the surface of the conductor itself. For M1 and M2, the charges plus Q1 and minus Q1 reside on the surface of the M1 and M2, which is shown here. See here. Here charges are present on the conductor, not inside the conductor. So the system has two conducting surfaces carrying equal and opposite charges, and these are separated by a dielectric. It is called a capacitive system. So this gives rise to capacitance. The electric field is normal to the conductor surface and electric flux is directed from M1 to M2 in such a system. There exists a potential difference between these two. Why? Because M1 carries positive charge and M2 carries negative charge. Let this potential will be, that is 1 and 2, that is V12. The ratio of the magnitudes of total charge on any of the two conductors and the potential difference in the conductors is called the capacitance of two conductor system. It is denoted by C. That is C equal to Q by V12. Q is the charge on the two surfaces, that is M1 and M2, and V12 is the potential difference between these M1 and M2. In general, it is written as C equal to Q by V. So where Q equal to charge in coulombs and V is the potential difference in volts, and capacitance is measured in farads. That is 1 farad equal to 1 coulomb per 1 volt. As the charge resides only on the surface of the conductor, it can be obtained from the Gauss law. Q equal to closed integral of d dot ds equal to closed integral of epsilon naught into epsilon r E dot ds. It is in the form of electric field intensity. So we can replace it by epsilon in E into ds. So as here V is the work done in moving the unit positive charge from one positive charge from the negative charge. So it can be obtained as V equal to minus integral line integral of E dot dl, that is equal to minus integral E dot dl. Positive charge to negative charge here. Hence, the capacitance can be expressed as C equal to Q by V. So Q is nothing but epsilon E into this equation, and V is minus E dot dl. From this, if the charge is increased, then E and D get increased by the same factor. So the voltage is also increased by the same factor. Thus, the ratio Q to V remains constant to keep the capacitance constant. So it is from the equation we can say that capacitance is not the function of charge, electric field intensity, flux density, and potential difference. So this is about the capacitance concept. So I have taken the references from V.U. Bakshi and A.U. Bakshi and also William Hayes. Thank you.